Good morning, Prof. We are P1 Group 2 presenting a comprehensive approach to mental health disorder classification. Our project builds on the research conducted by Kim in 2020, who proposed the model for mental illness classification from Reddit posts. They approach this task as a binary problem, classifying conditions like depression as present or absent. Likewise, we leverage Reddit's structured design with subreddit categories to accurately label mental health conditions. In our project, we extend Kim's approach by performing multi-class classification on posts, classifying 6 types of mental illnesses instead of identifying just one at a time. Throughout our presentation, we will highlight adaptations of the research to effectively carry out the new classification method. To effectively train our multi-class model, we first needed a large labeled dataset. Thus, we adopted an approach using publicly available Reddit archives which provided a lot of subreddit data. Each post was labeled according to its subreddit. For example, a post from a subreddit named anxiety would carry the label anxiety, which follows the approach in the reference research. While we adopted this method, we also considered an alternative labeling approach using large language models, which will then be discussed later on. Due to hardware constraints for training, we selected 1000 posts per subreddit, totaling to 6000 entries to create a balanced dataset for model training. Each post included its title, main text, and the subreddit label, enabling robust multi-class classification.
After data collection, data pre-processing is done to enhance dataset reliability for model training. Given the large data volume, we first assign class label to each data points by leveraging a large language model. To prevent misclassification from off-topic content, we ensure relevance by applying prompt engineering with COSTA framework. This system prompt iterates through the data frame, filtering out irrelevant data. We evaluated the LM effectiveness and we found that while the macro average increased by only 0.01 and the weighted average remained unchanged, it significantly reduced false positive. However, given its computational cost, the slight accuracy gain may not justify the overhead. We also perform text normalization by removing undefined, missing, and incomplete data, including entries where Reddit replaces deleted posts with delete or remove. Unwanted special characters and extra white spaces were also being cleared away. However, numbers are retained as they provide discriminative features, as shown in the 2 screenshot, and their removal reduced my audio accuracy by 2%. As we are training on word vectors, there's a possibility that the model performance can be affected by different word inflections. To allow more accurate text analysis for the model, we perform additional text normalization. Using NLTK, we split sentences into words and remove common stop words. For base word extraction, we explore 2 different approaches, stemming and lemmatization. Both methods reduce words to their root form, while there's a chance that stemming may produce a less accurate root word. We evaluate and assess the impact of these 2 approaches, and we found that in our use case, with a small dataset, lemmatization is much preferred with an increase of 0.01% in accuracy. This proves that lemmatization indeed provides a more precise output word form to allow model to perform text analysis slightly better. After data cleaning and text normalization, we proceed to prepare our dataset for model training, with feature creation by combining the title and text for each Reddit post to form a single input, before converting it to form numerical features. These serve as input variables for the model, while the model outputs an output variable represented class labels as integer. Afterwards, the dataset is split into 80% for training, 20% for testing, following the research paper. Finally, we set the row indices of these 2 separate datasets to ensure sequential numbering starting from 0. Before proceeding with training, we have to ensure that our data is balanced. While the research paper utilizes smoke to synthesize new data points for the minority classes, we do not use it as smoke-generated text may not accurately capture the linguistic nuances of users with mental illnesses. Instead, we address class imbalance by downsampling the majority classes. Also, state-of-the-art posting methods such as LightGBM provides a more effective way to address class imbalance. You can see the balance on the class label diagram that examines the distribution, confirming that it is not skewed, especially after scraping, cleaning, and balancing. Additionally, we generate a word cloud for each class to identify commonly used words in each subreddit, providing insights to their content.
Moving on to feature extraction, the input variable has to be converted into a numerical representation for training. In the reference paper, PFIDF is used to do so, but there is no mention of why it's used. In contrast, we evaluate 3 different vectorizers and embedding model to determine which works the best. The embedding model should perform the best as it is able to capture semantic relationships between words, while TF-IDF should perform the best among the vectorizers due to the IDF component. However, from evaluation, TF-IDF perform much better than all other methods, and it's likely due to the high importance of words such as depression. Next, we have to evaluate the appropriate model training method. The research paper uses XGBoost for the task, but with no mention of why it's used. Here, we evaluate selected classic models and ensemble learning methods. Some notable model selections include logistic regression, which does not work with multi-class by default, and therefore we use it using the 1 versus rest method, and also test multinomial logistic regression. The support vector machines is similar where we also use the 1 versus rest strategy. Moving on to bagging, we use random forests as well as extra trees, which is a variation of it, but it's said to perform better in high-dimensional data, which is useful for our case. For boosting, we evaluate methods like ADA boost and gradient boosting techniques. These are built on decision trees as a base learner which are efficient at handling multi-class problems, and in theory, these should perform the best for our task. After evaluating the models, among the classic models, multinomial logistic regression performed the best. For bagging, the methods perform the same with slight differences in the F1 score for each class. It is also observed that among the boosting methods, there is no significant difference across accuracy and macro average for the F1 score.
Additionally, we also use two more example methods which are well known for improving model performances and generalization. For voting, we use 5 models which performed similarly in previous evaluation. Voting managed to get 82% and 83% for hard and soft voting respectively. However, they still did not perform as well as multinomial logistic regression. For stacking, it blends predictions of base models, which is a more effective approach than voting. Hence, we conducted 2 experiments to evaluate their accuracy. The first experiment is a 5 low bias base learners with a high bias meta model. The second experiment is a 5 bias base learners with a low bias meta model. After conducting the experiment, it seems that logistic regression performed better, confirming that a high bias meta model blends predictions more effectively. After that, we expanded the model, making it a 7 low bias base learners with a high bias meta model without changing the evaluation matrix. It was shown that it took longer to train a stacking model with no change in overall accuracy, which does not justify the additional training time required for the 2 models. In the end, we decided to use a multinomial logistic regression which have faster performance, which compensates with only a small reduction in accuracy. Since the team has picked multinomial logistic regression, let's evaluate the model. We will explore its performance using some of the most commonly used methods. The goal is to understand how well the model generalizes and identify areas for improvement. Firstly, the tenfold validation gave us a consistent score across the 10 parts of the training dataset, showing that it has good generalizability without over or underfitting. Next, the classification reports an overall accuracy and macro average of 83%, performing quite well, with the F1 scores being relatively high. The confusion matrix looks very promising here. Almost all classes are well predicted with high true positives. Lastly, ROC curve shows an AUC score of 0.9644, showing us that the model distinguishes between classes very well. Here, we use the default threshold as 0.5 to balance precision and recall, but it is also possible to adjust it to prioritize recall or precision whenever needed. Overall, this model shows us convincing results in terms of the overall metrics.
We also touched on some additional features for the project, such as hyperparameter tuning for optimization. After comparing grid search, random search, and Bayesian optimization, we determined that grid search is the most suitable for our use case due to the small parameter space for both vectorizer and model. Firstly, the TF-IDF vectorizer already has predefined parameters like stop words and tokenizers, which were defined in the pre-processing phase, leaving only parameters such as n-grams and max features left to fine-tune. We also use grid search for tuning the multinomial logistic regression model, which only has L2 regularization, strength of regularization, and multi-class solver parameters. After evaluation for the vectorizer, we realized that while there is no change in the cross-validation accuracy, there is a drop in test accuracy by 0.01%, which concludes that the vectorizer is best used with the default parameters. For the multinomial logistic regression, there was a drop in accuracy in both cross-validation of tenfold and test accuracy by 0.01%, which also concludes that it is best to use the default parameters. Next, we use Lime to understand the importance of features and how they contribute to the model's prediction, which helps as most models are black box and do not show how they arrive to their results. We tried using Shep to analyze the interpretability of the model as well, but found it was struggling with pure text-based data and is more suitable for identifying relationship between features. Finally, the team deployed the model to make it publicly accessible. The toolkits used for the project is displayed in the table as shown. In conclusion, building upon the research paper with our own implementations, the team has evaluated each step and identified the following. For data preprocessing, we discovered that lemmatization had a slight increase in accuracy over stemming but has a higher overhead. As expected, TF-IDF performed better than count and hash vectorizers. We also tried out word2vec, which is a deep learning embedder, but it in fact performed worse than TF-IDF despite its overhead. For model training, we evaluated the classical models and found that multinomial logistic regression performed significantly better than the others. We then evaluated bagging, boosting, voting, and stacking to attempt to outperform multinomial logistic regression. In the end, we found that multinomial logistic regression outperforms bagging, boosting, and voting methods, but stacking has the best accuracy when 5 models are used. Hence, overall, multinomial logistic regression performed the best, and we perform our additional features on it. For our future work, we plan to do cross-domain evaluation, where we fine-tune our model with posts from various social media platforms like Twitter, since there is possible variations in linguistic patterns as compared to Reddit posts.